Lesson 13.1 is finding areas. So first we're looking at these velocity time graphs. So we have here a velocity time graph. It's the velocity in kilometers per hour over time in hours. And distance traveled can be found by finding the area under the curve of a velocity time graph, because distance is equal to rate times time, where rate is your velocity or your velocity curve, which is represented by whatever your y value is, and time, change in time, is represented by whatever your t value is. So if you want to find distance, you multiply the velocity by the time, which is the same thing as finding area in general. So for example, if you wanted to find the distance traveled of this velocity curve, the first 4 hours you can kind of represent it as a rectangle. So you find the area of this rectangle, which is 4 by 8. And then the second part is you can represent as a triangle with a base of 2 and a height of 8. And you can find all the area added up, and it ends up being 40 kilometers. So for these two graphs, find the area under the curve. The first one represents a velocity time graph like we just did, so you're finding distance traveled. And then the second one is more general, just find the area between the curve that they give us and the x-axis. So go ahead and pause the video and try these two. So for the first one, we needed to find the height and the base in order to find the area of the triangle. So I found the height by finding the y-intercept, so I plugged in 0 for x and got the y-intercept of our velocity curve to be 10. And I found the base by finding the x-intercept, so I set our velocity curve equal to 0, and I found that time was equal to 2, so our x-intercept was 2. So then we have just a triangle here, a right triangle, so we can do 1/2 base times height, where your height is 10 and your base is 2, and the distance traveled ends up being 10 meters. For the second one, we can kind of split this into two little pieces. We have a right triangle, and then we have a rectangle. So the first thing we needed to do was we need to figure out what A was, so we knew where to split this up. So that would be where your curve 1.5x has a y value of 3. So I plugged 1.5a equal to 3, and I found that a was equal to 2. So then for the first part of the area, I found the area of this triangle, 1/2 base of 2 times height of 3. And then plus, I'm going to add the area of this rectangle, which has a height of 3 and a base of 5 minus 2, which was also 3. So you end up with the area under the curve to be 12. So more generally, talking about area under the curve, when f is a non-negative function for some interval a to b, then we represent the area under the curve as this notation here. And it's read as the definite integral from a to b of f of x with respect to x, or the integral from a to b of f of x dx. And that represents the area under the curve from your curve to the x-axis from x equals a to x equals b, whatever that interval is. A is called your lower limit, and b is called the upper limit. So if we have this graph f of x, basically if you find the integral from a to b of f of x dx, you're finding this shaded green region right here. There's a few ways that we can do this. If there's something like the previous examples that they're easily split up into shapes that we can find the area of, then you just find the area just like we did in those previous examples. Otherwise, you can estimate area by splitting it into shapes like rectangles or trapezoids and have an estimation even if it's not an exact value. And then we can use our graphing calculator we'll talk about later, and then next section in 13.2 we'll talk about algebraically how to do them as well. So for this example, we have this graph of f of x equals negative x plus 6, and we want to find the area under the curve. It looks like between 1 and 4. So we want to write the definite integral, so that's something that looks like this. We want to write the definite integral that represents the area of the shaded region, and then find the value, which means find the actual area under that curve. So go ahead and pause the video and try number 3. So for the definite integral, we have our integral symbol, which represents sum because you're adding up area. And our lower limit here, we started at x equals 1, and our upper limit, we ended at x equals 4. And then in parentheses, you just put whatever the function is, so negative x plus 6. And then on the end, dx just tells you that you're taking the integral or the area with respect to the variable x. And then to find the value of the definite integral, that's just the area under the curve, so I split this into a right triangle up here on top, and then a little rectangle down here. So the area of this triangle would be 1/2 the base, which is 4 minus 1, which would be 3, times the height, which would be 5 minus 2, which is also 3, plus the rectangle, which would be 3 by 2. So I added all that up, and you end up with the area under the curve, which is the definite integral, to be 10.5. For number 4, we have the definite integral of -1 to 3 of x plus 4 dx. For part A, we want to state the function that's being integrated, the lower limit and the upper limit of integration. Then for part B, we want to sketch a graph of the function and shade the region that the definite integral represents, and then use area formulas to help you find the definite integral. So go ahead and pause the video and do number 4. The function that's being integrated is the function that's inside your integral symbol next to the dx, so f of x equals x plus 4. The lower limit is the smaller bound, the one that's on the bottom, so it would be x equals -1. The upper limit is the top bound, or the one that's on top, the bigger number, so x equals 3. So then x plus 4 is just a linear equation with a y-intercept of 4 and a slope of 1, and we want it specifically between -1 and +3. So this green region here is the region that we're finding the area of, or the integral, what that represents. So then to find the area, again, I split this into a right triangle that has area of 1/2 4 times 4, plus this rectangle that has area of 4 times 3, so the area under the curve is 20. To find exact values of integrals that we can't make nice rectangles or triangles or anything like that off of, we just use our graphing calculator. So there are two methods very similar to when we're doing our derivatives. So the first one is to go into math, and now we're going to number 9, which says function integrate, and then this will show up on your graphing calculator if you have a newer graphing calculator, and you fill in exactly what it says here. So whatever it says here, fill in the exact same thing. So your lower limit, your upper limit, your function, and then this is just the variable x. Hit enter and it'll give you your integral. The other method is if you already have your function graphed under y equals, you graph, go to second trace, which is calc, and then number 7 is your integral. It will ask for your lower limit, just type in whatever your lower limit is, and then it'll ask for the upper limit, type in that, hit enter, and it will give you your integral from there, and it'll even shade it on your graph. So go ahead and pause the video and use your graphing calculator to find the exact area under the curve for the integral 0 to 2 of x squared plus 1 dx. I used the first method, so I went math, number 9. I filled in 0 for my lower limit, 2 for my upper limit, x squared plus 1, and then this is again just the variable x. And then plugged that in my calculator, and I got 14/3, or 4.67. So the next one says consider the region A enclosed by the curve y equals -x times x minus 3 and the x-axis. Write down the definite integral that represents that area. So you might need to sketch a graph to see what that looks like, and then find the area of A. The first thing I did was I sketched a graph of this thing using my graphing calculator. So I have x-intercepts at x equals 0 and x equals 3, and it's a downward facing parabola. So we want the whole area that's being enclosed by the graph and the x-axis. So basically what I've shaded here in green. So that means my definite integral is going to be between these two intersection points, or these intercepts. So I'm going from 0 to 3 of -x, x minus 3 dx. So if you haven't already done so, go ahead and pause the video and find the area. So I used the second method because I already had this graphed on my graphing calculator. So I just went into second trace number 7, my lower limit was 0, enter. My upper limit was 3, enter, and it shades it nicely for me, and my integral, or my area under the curve, is 4.5. This next example says the area of the region bounded by the graph f of x equals x squared plus 3. The x-axis and the vertical lines x equals -1 and x equals a, with a greater than -1, is 12. So they're giving us the area of some region bounded where we don't know a. So first, pause the video and just write down the definite integral that represents this situation. So we have the definite integral from -1 to some unknown value a, but it's still our upper limit, of x squared plus 3 dx. And then they tell us that the area bounded is equal to 12. So that means that this thing is equal to 12. So now we're going to use our graphing calculator to help us solve for a. So we're going to go under math, And letter C is your numeric solver, and so this solves equations. So it'll come up, it'll say e sub 1, and it'll have a big blank box. On that, you're going to put in the left side of this equation here. Instead of a, you're going to write x. So it's going to say negative 1 to x of x squared plus 3 dx. So you're going to type in that integral just like you would if you were trying to evaluate the integral. And then under E2, you're going to put in the right side what it's actually equal to, which is 12. And then you're going to hit enter. And then it'll pop up and it'll show the whole equation inside this box. And then you're going to hit the upper right button. It's actually the graph button, and it'll make it solve. And it'll come up as x equals 1.99999, but basically if you round it correctly, it should be x equals 2, which actually means that a is equal to 2 because we were solving for our unknown value of a. The next part of 13.1 is the numerical method for estimating area under a curve, and it can be used either when you have a mathematical function, but also when we don't have a mathematical function to describe the area. And one way that we do this is by the trapezoidal rule. So we take our interval, and instead of breaking it up into rectangles, we break it up into trapezoids. So there's less over and under estimation. So if you look at this picture here, we took our interval under the curve y equals f of x and split it up into 4 trapezoids. So remember, a trapezoid has one set of parallel sides and one set of not parallel sides. So in this case, the base here is going to be on the height actually is going to be on the x-axis, and then the trapezoid, the other part, is going to be made from your 2 y coordinates here. The area of one trapezoid is the average of the 2 bases times the height. So 1/2 the sum of the 2 bases times the height, where in this case the height is the distance that's along the x-axis, the distance of that interval, and the 2 bases are basically the 2 y vertical heights. So if I want to sum up all these trapezoids, I'm going to have 1/2. I need to figure out what the height is, which is going to be the same for every single one of these. So it's just whatever my whole interval is, so b minus a, divided by n, how many trapezoids that I want. And then I'm going to sum up the heights. So these middle heights, 1, 2, and 3, they're always going to be doubled because you're using them for 2 different trapezoids. So for example, for trapezoid 1, you're using y sub 0 and y sub 1. For trapezoid 2, you're using 1 and 2, so you use 1 twice. So these middle ones you always double. The end ones you only use once. So you multiply by the first y coordinate, what they call y sub 0, and add that to the last y coordinate, whatever n is, how many ever trapezoids you're having, and then you have to double all your middle ones. So one way that we can use this is, like we said, if we don't have a function. So here we're just given a table of values and we want to estimate the area underneath the curve. And so we're going to split this up into trapezoids to help us do that. And now we need to multiply it by the bases of our trapezoids. So again, our end points are only going to show up once on our trapezoids, but our middle ones are going to show up twice. So my 2 end y coordinates, I'm only going to have them once, and then I'm going to multiply all my middle ones, 13, 10, and 3, by 2, because I use them for 2 different trapezoids, each one that they're paired with. So then if I plug all this in the calculator, I can estimate the area under this curve, whatever it is, as 61. For this next example, we want to estimate the area under the graph f of x equals e to the x over the interval 0 to 1 using 5 trapezoids. The first thing that I did was I actually just graphed e to the x between 0 and 1. So at x equals 0, anything to the 0 power is 1. At x equals 1, e to the first power is just e, which is about 2.7. So now we need to figure out how wide each of our intervals is. So if we're going from 0 to 1 using 5 trapezoids, we want to figure out the width, or basically the height, of each of our trapezoids. So the way that you find the height of each of the trapezoids is you take the distance of the whole interval, which was 1 minus 0, divided by how many trapezoids you're doing. So 1 divided by 5, which would be 1/5, or 0.2. So every unit of 0.2 is another trapezoid. So on my graph over here, I just kind of put those in there, so 0.2, 0.4, 0.6, 0.8, and I drew my little trapezoids in. So the area for this estimation is going to be 1/2 times our height, which we found to be 0.2, times the first and last y coordinates added up by themselves, and then 2 times all of the middle y-coordinates, because we use each of those for 2 different trapezoids. So go ahead and pause the video and try and finish estimating the area. So first I found each of my y-coordinates. So the first one, y sub 0, that's when x is equal to 0. Anything to 0 power is 1. The next y-coordinate is going to be when x is equal to 0.2. So I plugged in 0.2 for x. E to the 0.2 power is 1.22. And then if I move another interval of 0.2 over, the next one's going to be at x equals 0.4, and that was 1.49. If I move another unit of 0.2 over, I'm going to be at 0.6, which is going to be 1.82. And then if I move another 0.2 over, I'm at 0.8, which is 2.23. And then if I move another 2.2 over, we're at x equals 1, which is the end of our interval, and that's going to be just e, or 2.72. So then I filled all of those in. 1 and e are only show up once, so they're just added in the front, and then plus 2 times all the middle ones that show up twice, and our estimation of the area under the curve is 1.72. For this last example, we have the cross-section of a river, and the river is flowing at a rate of 0.8 meters per second. We want to use the trapezoidal rule with 7 trapezoids to find an approximation for the volume of water passing this point in 1 minute. So looking at our graph, this is kind of the ground that's underneath the water. So all of this right here is the water. So we're looking at the side view of it. And then here is a data table with each of these coordinate points laid out. So first thing, let's just use the trapezoidal rule to estimate the area under the curve. So go ahead and pause the video and do that. So the height of each trapezoid is going to be 1 because the distance between each of our x's is 1. So that's the width, which is really the height of our trapezoid. So I have 1/2 times the height, which was 1, and then the first and the last y-coordinates by themselves, because they only show up in one trapezoid each, plus 2 times all of the middle y-coordinates, because they'll show up in 2 different trapezoids. So the area under the curve is 14.8. So in context of the problem, the area under the curve is what I've highlighted here in yellow, which really isn't the water, it's really actually the ground underneath the river. And we want to know the volume of the river. So now we need to figure out, well, if 14.8 is the area of the ground, what would the area of the water be? So go ahead and pause the video and see if you can figure out what the area of the water is. So the area of the water would be everything that's not the ground, basically. So I found the area of this entire rectangular cross-section, so 4 times 7, and I subtracted the area of the ground from it. So I ended up with 28 minus 14.8, so then the area of the water is 13.2 meters squared. So this is the area, and we can find the volume by how much water is flowing through given a certain amount of time. So they give us how fast the water is flowing, so we can use that to help us find the volume. So we want to know the volume per minute, basically. So we have the speed per second, and I multiplied that by the area, so 13.2 meters squared times 0.8 meters per second. So now we have meters cubed in the numerator, which is what we want for volume, but we want it per minute, and right now it's per second. So now we need to convert it into minutes. So I'm going to multiply it by 60 because there's 60 seconds in a minute, and this will give us the total volume per minute. So if you multiply 13.2 meters squared by 0.8 meters per second by 60 seconds, you end up with a volume of 634 meters cubed per minute passing through this cross-section. So this has been finding areas and estimating areas under the curve using composite graphs and trapezoidal rule, and then also finding exact values of integrals using your graphing calculator.